Let's get started with our unit 5 material. Just a quick thing before we start though. This is a preview of our formula sheet. So I'm thinking about just putting it like this, where I kind of give you like specific rules and definitions. So you don't have to memorize too much of these. The only thing I will say Um, for these is that just because you have the rules doesn't mean you need to dictate the notes. You still need to dictate the notes. I mean, your answers, excuse me. And then also, I'm thinking about still like putting on the putting on the question converges or diverges, and then you should use the blank test, or maybe I'll put like dealer's choice depending on what it is, but or maybe I'll ask for specific ones. So just like little tidbits like that, just to make sure you know how to use them, and then explain reasoning at that point as well. Let's see. Yeah, I even included P series definitions. Um, I think the only thing I didn't include was the harmonic series, but I kind of just lumped it together with the P series because if it's harmonic, then it's just a P series with P is equal to 1. And then if it's the alternating harmonic, then you would jump here first. Hmm. Excuse me. So just keep this in mind while you are doing the review that's assigned today. There's no worksheet. There is still homework, but um, I figured let me do some kind of trade-off and just not put a worksheet for today. Okay. All right, so let's go unit 5, 5.1 power series and functions. Some common functions used in calculus and pre-calculus are linear, quadratic, or cubic. These are special cases of polynomial functions, which include terms of whole number powers of x up to some larger power. So we would have, this sort of organized layout of us just starting with the lowest and then moving to the highest power. If we now let terms continue indefinitely, so say we don't put a bound on the highest power, we create a new type of function called a power series function, such as this guy over here, where we keep adding x as it's being taken to the power. We keep adding, not, I mean, combining x, but this time we put a coefficient in front of it, where every other constant is negative, and then we have the 1 over, well, okay, we would probably put 1 over 1, 1 over 2, 1 over 3, 1 over 4 to match its power. Here we're doing the same thing where it's alternating, but then we're doing a factorial, and now we're only counting even powers. So these are all power series with some like little twists here and there for G and H. So the power series is a function of the form here, where we're counting up the x's and it's each being multiplied by some constant defined by some technical rule. So that's why it's indexed as n. We can create similar functions by performing a horizontal shift from algebra. If a is a constant, then g of x is equal to f of x minus a. This would be called the related function. And then the adjustment we make from here to here is just x minus a. So again, horizontal shift. So this is a part of your um like transformations lecture that you saw in pre. Hold on, I'm gonna sneeze. Hopefully I muted that. This is part of your pre-cal lecture, your transformations lecture that you saw in pre-cal. So those ideas keep that in mind. This is called a power series centered at x is equal to a. So it talks about where on the graph it is centered. This is a very important piece of information that we're going to use basically throughout this whole 5.1. Now, before we get into the nitty-gritty of it, let's go ahead and just go over real quick solving absolute value inequalities. So don't forget values like less than and greater than, an open circle, and then parentheses. These all infer when something is so close to that number, but not exactly that number. Then we have the less than or equal to, greater than or equal to, a closed circle, and then brackets. These just mean at exactly that number. It can equal. Here, it does not mean it can't equal that number. And then solving. So if I have some expression here where it's a times the absolute value of this linear idea is less than c, then we would write a version of this, or okay, wait, first we would divide out the a. And then I would write a version of this where it's positive and then negative. Now because it's less than, you can technically see it like this and like this, but because they're flowing the same way, you can just write as one sort of inequality expression. Here, though, it's a little trickier to do that, so that's why you split into two, where you keep a positive one and then you keep a negative one. Because while you're keeping the positive negative one, you're switching the value. Excuse me, you're switching the orientation. So this flips when it's negative, this does not. Same thing here. This did not flip when it's negative, this did flip when it was negative. Then equals, it's a similar vibe, but you don't have to worry about flipping anything. You just have to make sure you recall keeping it positive and then keeping it negative. The equal sign is equals, so you don't have to worry about that. All right, that's just a quick little review in case we didn't recall how to solve for an absolute value. Let's go ahead and do some of these problems. So we're gonna start with this one. This one's almost gonna be sort of, it's gonna be, it's a little silly sounding, but it's gonna help us build this world and help us see, something to be seen. Okay, consider the power series function here. This is our coefficient, and it's x to the n. The value of f of x exists whenever x is a value for which the series converges. So now we're back to the idea of convergence. However, our sum is now an expression of a function. We write it like this, and in fact, we've been writing it like this for this whole section, because x is customizable. N is the one where we are actually taking the time to index. So it's a bit different. Okay. What this implies also is if x is customizable, then that means it relies on x, whatever we plug in x to be, to see if the series actually converges, if it actually equals something. The function does not exist at any x where the series diverges. So remember convergence and divergence, that's still going to be important here. If it equals something or like an actual entry, then it's considered to be convergent. If it doesn't equal an entry, then it's divergent. Determine whether or not the function exists at the given x. So we have x is equal to 0. Okay. So this is almost like a little trick question because, well, if I do x equal to 0, well then all of these will be 0. And they kind of just cancel out organically to 0. So f of 0, the only one that doesn't seem to cancel out is when it's when n is 0. So just that one entry. So f of 0 is 1. And I mean, it equals something. It's kind of trivial, but it does equal something. So therefore, it is convergent at x is equal to 0. What about x is equal to 1? Well, here we can see that it's 1 plus 1/2 plus 1 over 3, uh, 1 plus 1 over 4, 1. And all of these, they don't cancel out, but they're sort of trivial. They will all just go to 1. Because we know 1 to the power of anything is just 1. So really, you're just writing 1 plus 1/2 plus 1 over 3 plus 1 over 4 plus dot dot dot. And a way we can, the formula sheet, a way that we can see this out to be is we can basically rewrite this as the p-series notation, 1 over n to the power of, well, 1. From n goes to, well, it says 1 to infinity, but we have plus, or, oh no, this would start at 1 by happenstance. Yeah, okay, my mistake. But we know that because this is a p-series where p is equal to 1, this would be divergent. And the divergence implies that this function does not exist. This function itself does not exist. More specifically, the sum of this would technically go towards infinity. So f of 1 would go towards infinity, which is not plausible. It's just not possible. Because infinity is a constant. And your logic is that it's a p-series. Let's jump here. X is -1. So now we have -1, -1 squared, -1 to the power of 3, etc. For here, I'm going to choose to make the simplification to rewrite this as like the p-series, but with the alternating term. So if I do n is equal to 1 again, infinity, I'm going to write first the 1 over n, so I don't have to think about it. But it starts positive, then it flips to negative, then it starts positive and it flips to negative. I can get away with writing it as -1 to the power of n plus 1. So I can make sure that it first starts as a positive, and then for when n is 2, it will come back to negative, and positive, and negative. And here we have the alternating series, or you have the alternating harmonic series actually, but we can do the alternating series test here. Or for the alternating series test, you just have to check if it's decreasing and if the non-alternating part goes to infinity. So the limit, goes towards 0 as n goes towards infinity, which it's bottom heavy, so it definitely does. And then what am I saying? There's an alternating part. Oh, decreasing. I'm looking at the formula sheet at this point too. Might as well. 0 to 0, and then it is decreasing. Okay. And also, I'm gonna put this on like number 6 as extra, so just keep that in mind, okay? So you should be able to see this formula sheet today as well. Um, so we need proof that's decreasing, which we've done this proof before, but I'll do it again. You want to double check that the n plus 1 is less than the 1 over n. You can just cross multiply to get n is less than n plus 1, which is just true. So therefore, it converges. And then if you said it converges via the alternating harmonic series, that's fine. But if you said it converges via the alternating series test, then that's fine as well. Oh, and then I guess I should write that what is the sum? I guess we don't need to know the sum. I think I just some happenstance that we were able to figure out for these two. For this one, technically you don't need it. Because really, that's not what the question's asking. It's just asking, do you know it's convergent or divergent? And we proved it is. Okay. Now, that is super tedious in the context of if we are to tackle every X entry, right? There's a fault in there. Every X entry is not limited to whole numbers, and it's not limited to any specific interval. We are just literally testing 0. And then if we need to go into decimals, we do 0.1, 0.2. Or what if we need to go into further decimal, 0.01, 0.02. And that is obviously, excuse me, I burped. That is obviously cumbersome. We don't like that. So instead of checking the value of x one at a time, we can instead use the ratio test to examine most values of all x at once. Consider the power series function here. This function, the center of this function is 3. Yeah. And the series for sure converges when x is equal to 3. For which other value of x does the series converge or diverge? We're going to find this out via the ratio test. Now, oh, and then for which values of x is the ratio test inclusive or inconclusive? Now consider the technicality of the ratio test. Converges absolutely, diverges, or is inconclusive. If we find out the L term, then we could set it to each of these 3 equations, or 4, technically, but this one is just a technicality that we may be able to gloss over. Okay, so let's go ahead and do the ratio test. It's defined here. So we're doing the ratio test. The limit as n goes towards infinity of the n plus 1 version of this. So n plus 1 times x minus 3. So then n plus 1 over n. And then, let me see, x minus 3 to the power of n. Okay, from here, we know that this part of the fraction is allowed to not escape the limit, but escape the absolute value because we know n is going to start off to be a positive value. So we can get away with this. Let's go ahead though and actually write that out. So the limit as n goes towards infinity will have n plus 1 over n. And then what's left over here is, right, the x minus 3 to the power of n plus 1 over x minus 3 to the power of n. But we see that this will cancel out, and this will cancel out, but leaving 1 x minus 3. So limit as n goes to infinity of n plus 1 over n and the absolute value of x minus 3. Okay. From here, whatever this value is going to be is not relevant to the end. So it almost behaves like a constant in which we can take out that limit. So absolute value of x minus 3 times the limit as n goes towards infinity of n plus 1 over n. Now this is just a balanced equation. So we take the coefficient top and the bottom. They're 1. 1 divided by 1 is 1. So taking the limit, you just have the absolute value of x minus 3 times 1. And that's going to be your answer, x minus 3. Now keep in mind, all of this is to find L. So at this moment, L is equal to the absolute value of x minus 3. Now you need to figure out, because the prompt said so, converge and diverge, and inconclusive. So we need to set this L to 4 things. Okay? We need to set this L to be converges, absolutely. That's going to be give me a second. Let me see something. I'm just noticing that think I forgot the absolute convergence test. Okay, I need to. I think I need to include that. Okay. All right. I'll include that later. So the one you will see you will not just have this. Okay. Um, converges absolutely. We know that just when L is less than 1, so that means I'm going to set x minus 3 to be less than 1. Solving for this inequality lets me split. -1 is less than x minus 3 is less than 1. And then plus 3. So what is that? 2 is less than x is less than 4. Okay. And then we have diverges. So that's two equations. It's going to be the absolute value of x minus 3 when it's greater than 1. So that's let me split up to when x minus 3 is greater than 1, or x minus 3 is less than a -1, x is greater than 4, x is less than 2, and then for when the absolute value of x minus 3 is equal to infinity, this one's almost kind of the dummy one because there's really no number x value where it's automatically considered infinity. If you take a limit, sure, but this one really leads to nothing, so we kind of can't do any here. It's a dud. And then lastly, inconclusive. It's just when it equals 1, which is going to have the exact same format because we're just been messing with 1. We have x minus 3 is equal to 1. Oh, sorry about that. X minus 3 is equal to -1. Add the 3 to both sides, you get 4, and you get 2. So the values when it diverges, inconclusive, converges absolutely. Let's use this conveniently placed line. So this is 0, 1, 2, 3, 4. Here, I'm gonna do 5 as well. you have for converges absolutely, we'll have the period from here to here, but with a circle defined at the ends. For diverges, you would have all the values less than 2 and greater than 4, but not including them. Again, it's a circle there as well. Oh, I forgot to highlight this as well. I mean, it led to nothing, so that's why I guess why I instinctively didn't highlight it. But and then the inconclusive parts. So those would just be the bullets 2 and 4. Right. Now, a couple of things. So at this point, there's gonna be a style of questions you're gonna get asked. Let me just sneak to the future real quick. You're gonna get asked for the radius of convergence, and then the interval of convergence. Here, you're just looking at the convergence area, which we have just denoted in this green line. The radius, recall radius is half of the length of the diameter. The radius here is just going to be 1. You can see that visually here as well when we just have the absolute value expression. Or you can just see that after you do the inequality and you chop that distance in half. 4 minus 2 is 2, and then chop it in half. 2 divided by 2 is 1. And the interval convergence, where did it converge? Well, we saw it converge specifically at 2, comma 4. But, and the caveat here for the but is that we don't know if, oh, I already did it, my bad. We don't know if at 2 and 4, if it was actually convergent or not, because it was just inconclusive. So you can quickly view the expression at 2 and at 4. If you plug in, let's do that on the side, x is equal to 4, then you have the expression to be n times 4 minus 3, which is just 1 to the power of n. So the sum of n. And the sum of n, as n goes, is from 0 to infinity, and goes from 0 to infinity. That's just you adding n a bunch of times. So we know that that's just going to go towards infinity. So that means it is not convergent at when x is equal to 4. Let me see. And then for when x is equal to 2, that means you'll have an alternating series because it would be -1. So -1 n to the power of n. This has a similar vibe, but instead of you just kind of evaluating the limit, you would do the alternating series test, and you would just look at this guy, and you would see that the limit as n goes towards infinity of n, once again, is just going to be infinity. But this means it fails the alternating series test. Here, let me write that. It fails alternating series test, but passes by accident the divergence test. So again, that'd be another parentheses. Is that going to be the case for all of the x is equal to the inconclusive part? No. But it's just something that you have to evaluate. All right. For any power series function, written like here, the values of x the values of x for which the series converges is called the interval of convergence. The power of the series always converges when x is equal to a, at the center of the power series. Because when x is equal to a, we get this expression, which is just equal to CO, because all these will zero out. The radius of convergence is the distance r from the center of the interval to each endpoint. Another one. Example 2. Find the radius, center, and interval convergence of the power series function written here. Well, the center is a trivial one. It's already given. It's when x is equal to 1. So the center is when x is equal to 1. Yeah, I'm not going to write is equals. Is x equal to 1? That's the first part. So then we need radius and interval. Okay. Ratio test. Let's go. So for the ratio test, we have the limit as n goes towards infinity for n plus 1 first, so 2 to the power of n plus 1 times x minus 1 to the power of n plus 1 over the square root of n plus 1 times, and then just the opposite of an, which is square root of n over 2, and then times x minus 1 to the power of n. Okay. I'm going to take advantage of canceling things out. Oh, wait, hold on, I forgot n here. So we see that cancels out, and this cancels out, but not the 1, so it just leaves a 2. This cancels out, and with this, but leaving the leaving 1, x minus 1, and then this really doesn't do anything for us. It can't even simplify. Also, so we're gonna go ahead and just well, the ends can escape the absolute value, but it cannot escape the limit because it's part of the limit. And then the 2 and the x minus 1, the 2 can escape the absolute value and the limit, but the x minus 1 cannot escape the absolute value. So our final form should be 2 times the absolute value of x minus 1, and then times the limit as n goes towards infinity of the square root of n over square root of n plus 1. For these guys, let's see what we can do. Well, I'm gonna just go ahead and cheese it a little bit. So there's a lot of ways I can solve this limit, technically. I just write it under one whole square root. And we know that the limit of inside this guy. Oh, wait, I forgot to write the rest of the 2 times 2 times x minus 1. So 2 x minus 1 bar 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 times the square root of the limit as n goes towards infinity of n over n plus 1, which here is just going to be 1, and then the square root of 1 is 1. So really you're left with 2x minus 1. You can write times 1 if you want, but we know what that simplifies to. So now they asked for when it converges. So that means we really only have to check when this L, which is what we found, is less than 1. So 2 absolute value of x minus 1 is less than 1. We can't do anything here until we get the absolute value by itself. How do we get the absolute value by itself? Well, dividing by 2. So the absolute value of x minus 1 is less than 1. From here, we should be able to already visually see that our radius is going to be 1/2. So I'm going to write that already. And I'll just have the interval confirm that when we have it. So let's go ahead and do this. We have x minus 1 is less than 1/2, and then is greater than negative 1/2. Add the 1, we get 1/2 on the left, and we get 3/2 on the right. Okay, so on the number line, if we do 0, and if we do 1, and if we do 2, then our interval would be from here to here. And we can see how the radius is like 1, so half of 1 is 1/2. Now, the only thing we have left to figure out is what happens when x is equal to 1/2 and x is equal to 3/2. So let's see. Okay, so when x is equal to 1/2, we have, I'm going to write it out in full just because I don't want to miss anything. 2n square root of n, and then it's going to be 1/2 to the power of n and negative 1/2, right? Yes, okay. So because they share the same power, we could combine them. Oh, that's funny. And then we would just get around the side negative 2/2 to the power of n, and times 1 over square root of n, which that just simplifies to negative 1. And that's 1 over square root of n. And then this is just an alternating p series with well, alternating series tests. Mm, maybe not alternating series test. Or actually, yeah, you're better off just saying it's an alternating series test. It is a p series. Oh, you know what? It's going to be p series when it's relevant for when x is equal to 3/2. So you can just say alternating series test because we're taking the limit as n goes towards infinity of 1 over square root of n, which we know is bottom heavy, which is just 0. And then is it steadily decreasing? Yeah, you'll get 1 over square root of n plus 1 is less than 1 over square root of n, cross multiply, n is less than n plus 1, square root, square both sides, n is less than n plus 1. So that checks out. So converges via alternating series test. And then for when x is equal to 3/2, that's going to be 1/2, but positive. So we have 2n, 1/2, n over square root of n. That combines into 2/2n, which is just 1, which anything to the 1 is equal to, or 1 to anything, excuse me, is equal to 1. And that's just going to simplify to this here, and then we know that that is just a p series. P series, and p is 1/2, which is less than, uh, what the? Did you all hear that? So for context, when I asked a question, the iPad behind me answered. That's super freaky. Okay. What was I saying? Whenever it's less than or equal to 1, it diverges. So that means we have a similar situation where um, the interval is, let me see, for x 1/2 is going to be a bracket at 1/2, and it's going to be a parentheses at 3/2. So similar, but not exactly. Here, we had them just both fail the test, but we had the similar logic of checking the 1 and -1 part, but this leading term kind of did shake things up. Okay, let's see. Oh, forgot a box. So all three of these are my answer. Okay, now some trick question setups. So if the ratio just produces a 0, I forgot why I included wrote that, but if the ratio just produces 0, then the power series converges for all x, since when you do 0 is less than 1, that's just a fact. It's not dependent on any x. So the series already converges at a. So that tells me specifically that I'm on some, 0. And irregardless to, let's put a just over here. That tells me that no matter what on this number line, I would mark the whole thing. Wait, what are we using to do convergence? The green. So I would mark the whole thing as converges. Then the interval would trivially be considered all values, so -infinity to infinity. And then the radius, well, it's kind of a trivial fact. It's going to be infinity because you can't really take half of infinity. Um, or you can take half of the length from infinity to -infinity. So that's just another infinity. If the ratio test produces infinity, and you set that to be less than 1, then by that logic, that's just not true, right? Infinity, that concept, will never be less than 1. So therefore, if you're on some number line, 0, and let's make a here, it's really going to diverge for everything but this specific little sliver when x is equal to a. And it diverges when it does not equal a. So it converges only for that little sliver of a, but it diverges elsewise. The interval of convergence at this point is, you can just write it as, I think I don't want to confuse notation, but you can technically in the notes, it's written like this, which I don't like because it's using the series brackets. You can say A, or you can do A to A, which is trivial, but at least this one, hold on, I need to mute my phone. But this one makes way more sense in my opinion. Okay. And the radius is 0. Now, the radius is 0 because really it doesn't exist. There's no like length of convergence. So the radius, even though the length is super tiny, it's better approximated to be 0. Let me just double check because that's always confused me when I was learning this because I remember thinking to myself, like undergrad, I remember thinking to myself, like, well, there is no radius, so isn't it like my head would go to does not exist sooner than it would go to like a number, but no, it is 0. Okay. All right. Okay. How far along are we? We gotta keep it moving because yeah, we got 6 more pages. Let's go. Okay. All right. Find the center and interval convergence for the power series function written here. Okay. So let's go ahead and just do this. We got as n goes to infinity, uh, fact n plus 1 factorial x minus 2n plus 1 divided by 3n plus 1 times 3n over n factorial x minus 2n. Okay, that cancels out and escapes the whole thing. 1 over 3. This simplifies to just n plus 1, which doesn't escape the limit. And then this cancels out to x minus 2. But it can escape the limit, but it does not escape the absolute value. Of n plus 1 over... Oh no, it's just n plus 1. Force of habit to write it over something. So in that case, the limit of n plus 1 is technically infinity. Or, if you want to be super specific, infinity plus 1. But that's just going to be infinity. But you'll see how this whole expression technically goes to infinity. So even if you would begin the prompt, okay, well, this is L. So infinity is less than 1. That doesn't give you anything. So therefore, this is a trivial sort of situation that was mentioned up here. It was specifically this guy. So that means that you can right away say that while you have the center is 2, which is something I should have answered before because we didn't need to do all this before. The interval convergence and the radius, the interval is 2 to 2, or you could have said, the entry A. The book uses, I mean, the entry 2. The book uses this. I just don't like it personally. And then the radius is 0. And you're allowed to stop here because you get an L of infinity. How about over here? I wonder what we're gonna get here. Well, let's see. The limit as n goes to infinity of the n plus 1 entry. So we have -1, n plus 1, x, n plus 1 over 2n plus 2 of infinity. I mean, of factorial, and then times 2n factorial -1 n and then xn. Okay, well, these cancel out to just be an x on the top. These cancel out to just be a -1 on the top. And then this will interact and just leave on the bottom a 2n plus 2 and a 2n plus 1. So the -1 under the absolute value disappears. The x does not, but it can escape the problem as a whole. And then the limit, as n goes to infinity, has 1 over 2n plus 2 over 2n plus 1. From here, it's sort of trivial to see that you would just, distribute the bottom, and you would get just a 2-degree polynomial on the bottom. There's a 0-degree polynomial on the top, so that whole limit should equal to 0. So you have x times 0, which doesn't matter what x is, anything times 0 is 0. And here you have another trivial case where the limit is equal to 0. So that means that you can right away answer the following. Oh, I forgot to enter center again, but center is 0. We didn't need to do all this before. We could have just visually see that because the x is there mentioned. The radius is infinity, and the interval of convergence is from negative infinity to infinity. And those would be your answers. So now let's add a step of the difficulty. So we are dealing with power series, and they have a technical limitation. The limitation is that for a power series, it's sort of trivial in that really what you're dealing with is you're dealing with like this common, linear system, or you're provided with the series or the sum of what you want in the prompt. But what if you wanted to be even more custom than this? So that brings us to the logic of finding power series of other functions. The prompt's a little bit different though. I did a little different intro than in my notes on what I said out loud right now, but it still obviously leads to the same point. Let's go. How does a calculator find the numerical value of cosine of x? Calculators know something we don't yet. There's an algebraic type formula for the cosine function, seen here, where cosine of x is just a power series function. The series here is a geometric series, with specifically that the first term is equal to a, or is equal to 1, and the common ratio is x. So, if the absolute value of r, which in this case we're labeling as x, is less than 1, the series converges and sums up to here, 1 over 1 minus x. This is a power series for the formula 1 over 1 minus x. So we have just made this sort of power series put together with the geometric series. So don't forget the geometric series mentioned here. Instead, a is 1, which is why the sum is 1, and then r is our customizable x. If if the absolute value of x, check 2 for yawns. If the absolute value of x is less than 1, the whole series converges and it has a sum. So now we're going to manipulate what we know to create new series. We can use substitution and other algebra steps to create power series formulas for similar functions. The general idea is any expression of the form 1 over 1 minus u can be written. So we have 1 over 1 minus u is equal to the sum of un plus all of these u. So I basically copied and pasted this. But what's utilized here is the idea of u substitution. So don't forget u substitution from when it was first introduced, probably in your pre-cal classes as a sort of manipulative trick, but it's not u substitution like for integration, where you do u and du. So example, find a power series formula for each function with a center at with a center 0. Identify interval convergence in each case. Okay. So for here, we have 1 over x squared minus 1. Really, the algebra of making it look like this would be to just flip the bottom and then to do a double negative situation. And that way, we say u is equal to negative x squared. 1 over minus u. And then we introduce the summation. The summation as n goes to infinity, as n goes from 0 to infinity of un. and you just plug in back u. Parentheses negative x squared n. Um, Now there's technically nothing wrong with leaving it like this. Um, but in reality, you're better off simply just reevaluating the problem. -1 to the power of n, and then x to the power of 2n. Just because it allows for that more of a, I'm gonna call it allows for that more specific parts to come out, and it allows for more accurate testing. So, in this case, though, we have our answer. Now, let's see. So we found a formula. You could either left as here as here. But the second part says identify the interval in each case. Okay? Or call the notation of that x being less than 1. So similarly, that u, the absolute value u is less than 1. What did we say u was? Well, we said it was negative x squared. So we're saying negative x squared instead of u is less than 1. From here, um, what can you simplify? Well, you really can't do too much with this because for here, you know that you get the negative out. And then while you could technically split it up like this, you get from, what is it? -1 is less than x squared is less than 1. The issue here is that we know x squared, because of what it is, will never be negative. So really you can trim this to be 0 is less than or equal to x squared is less than 1. And then from here, you would see that it converges for all these values. So you would just write the interval as, oh, sorry, brackets, 0, comma, 1. Let me just double check. Do you have to evaluate for when it equals 1? Well, for when it equals 1, you could still technically do the alternating series test, and you do not get, so this will diverge because it does keep doing the flip-flop of minusing 1, adding 1, minusing 1, adding 1, minusing 1, adding 1. So, yeah, I think you don't have to worry at this point anymore about checking if the 1 is. You could just follow this rule to a T. Okay. Alright, let's keep it going here. Okay, so here we have to do a little bit more manipulation. We got 2x factored out. And then from here, we technically have to factor out 1 over 4. So I'm going to do that. We have, well, in that case, that makes this 1/2 x. And then we have 1 minus x over 4, which in this case, our u is just x over 4. So 1/2 x, 1 over 1 minus u, which we can rewrite this portion and only that portion to be the summation n goes to 0 of infinity of u to the power of n. Then we plug in that u back, 1 over 2 x summation. Oh, I forgot about the x, excuse me. Of x over 4 to the power of n. Then from here, what more simplification can you do? Wait, what the heck? Why did I flip it? Wow, I didn't. Oh, I know why, because I took out 1/4. That's right, that's right. Okay, I got worried. So from here, you get the summation of, you can leave the 1/2 out if you want, but I would just put the x back in. You would get xn plus 1 over 4n. Yeah. I'm trying to think, what else could you do? And you can also rewrite it with the 2 going inside to be xn plus 1 over 2 to the power of 2n plus 1. Because you include the 2, and this is just 2 squared. But really, in my opinion, you could stop here if you wanted to, because it's really where the meat of the problem is. So the meat of the problem is really just here. In that case, though, you could box in this answer or any of these other alternations I made, that would be full credit. But now we have to do the interval. So we have the absolute value of x minus 4, x divided by 4 is less than 1. You could do two things. You could know that because this is a multiplicative property, you could factor out the 1 over 4 already. Here I'll do that in 2 arrows just so you know what you could see what I mean. But you still should get the same interval no matter what you do. If you just do the split already, you'll get -1 is less than x over 4 is less than 1. And then you just multiply by 4 to get x by itself. You'll get -4 is less than x is less than 4. And then for here, oh wait, I'm using blue. I'll use red. If you first factor out the 1 over 4, which you can because it's positive in a multiplicative factor, and then multiply by 4, and then solve for or set the inequality, you'll still get the same value. And then you still get the same interval. -4, comma 4, parentheses, parentheses. Okay. Uh, Let me just see. Hmm. Okay. All right. Let's go ahead and move on to the next pages. So now we're going to get even more custom about it. So manipulating known series to create new series of differentiation and integration. So if we know that this function is defined as this power series, then we could do a derivative. And because of the additive property of derivatives, we can just derive the entry in here, and we can go ahead and rewrite it like this, where we include, a power rule and then every c gets moved a level to the left. So c0 will disappear because we know derivative of a constant is just 0. And then c1's by itself now, and then c2 is next to the x, but then there's a 2, and so on. And then you could you could write n is equal to 0, but we take the convenience of n equaling to 1 now, because again, that c0 disappeared. If you do n is equal to 0, then you'll still have a 0 multiplying everything, but it's dealer's choice, really. That I copied. Okay, so example 2. Differentiate both sides of the power series formula. So we have these two guys, and then it says to construct this formula for 1 over 1 minus x squared. Okay, so for here, I'm going to perform the derivative of both sides. I guess, let me do the left-hand side first. So derivative of 1 over x, or sorry, wrong, 1 minus x. Before I even do derivative, I'm just going to rewrite that as a power, just so I don't mess myself up. Do power rule, so I get a negative 1 minus x to the power of negative 2, and then times the derivative of what's inside, which is just a negative 1, which will cancel out the negatives, and you left with 1 over x minus 1 minus x squared. Okay. And then for the right-hand side, well, that one's a bit trivial, but I'll still do it like separately. Right-hand side, you're doing summation. This goes from 0 to infinity, x to the n. You know, it's just a general notation of a power rule. So that's just going to be summation, and goes to infinity. Or actually, you could do one more step, which is that you know that you're only taking derivative of this, what's inside, because of the additive property, and then you write the answer. N x to the power of n minus 1. Okay, so then your answer is 1 over 1 minus x, all of which is squared, is equal to summation of n x n minus 1 from n is going to 0 to infinity. And then here you also have the luxury of starting from 1 because you know n, when it's 0, times anything will just be 0, but it's not a bad thing to just have it. Let me see. Okay. Now suppose we know this function is equal to this power series. If we integrate both sides from 0 to x using a dummy variable integration, what should we have as the following? So, let's go ahead and set that up. We're using a dummy variable, so I'm just going to go and use t, 0 to x, f of t is, I'm still going to do like left-hand side. So I'll just start there. Okay, this is a bit trivial. You just do the calculus x and then minus f of 0. And for the right hand side, this is where we do some maybe a little harder work. You would do the integral from 0 to x of the summation of cnxn, just from 0 to infinity. The integration can escape in the inside because it's just a bunch of adding terms. Oh, t dt. And then integration 0 to x of cn tn of dt. So you specifically get the summation of bracket of Cn Tn plus 1 over T plus n plus 1 from 0 to x. Okay. If t is 0, then the whole thing cancels out. So you can't really do this of x minus this of 0 because 0 will just be nothing. Minusing 0 is just that. So really, you could only really need to plug in x. Cn x to the power of n plus 1 over n plus 1. And your final answer is capital F minus f of 0 is equal to the summation n goes to 0 to infinity of Cn x n plus 1 over n plus 1. And that's going to be your answer here. I forgot to box that answer over there. So, with this known, then we can construct the formula for the antiderivative of f of x. If we were asked to do this, we would just simply add that f0, the capital F of 0 that we had previously over here. So, now knowing that these exist, we can use setups for calculating more specific functions, utilizing the potential of their antiderivatives. So, recall that, or let me write example 3, or say example 3. Integrate the power series formula from 0 to x to construct the power series formula for ln of 1 plus x. Now recall that the derivative of ln of 1 plus x is just simply 1 over 1 plus x. This does not let us use the power series idea. This does, namely, we do 1 over 1 minus a negative x. But from here, we can use that power series. But if we were tasked specifically to get ln, then we would have to integrate. So I'm going to integrate from 0 to x, and I replace every mention of x with t. So let's do left-hand side again. 1 over 1 plus t dt. Hold on, give me a second. I could do u substitution for this, but because I cheesed it a little bit by noting it here, then really I know that this is just going to be ln of 1 plus t from x to 0. And then from here, you're allowed to plug in x and 0 respectively. You have ln of 1 plus x minus ln of 1 plus 0, which that will be 1. Ln of 1 comes out to 0. So really, this whole thing cancels out on the left-hand side. On the right-hand side, you would, I'm already going to skip the step where you let the integration sneak in. So sum of n going to 0, infinity. I'm gonna let this escape too because that's not using our variable of integration. So we have the integral from 0 to x of t to the n dt. And then from here you could do the integral you have t to the what was it, n plus 1 over n plus 1 box with x and 0. When you replace it with 0, it'll cancel out, so you just put back the x. -1 n, and then x to the n plus 1 over n plus 1. And none of these escape because it's n plus 1. But that's basically your answer. So your answer is ln of 1 plus x is equal to the summation, as n goes from 0 to infinity, of -1 n x n plus 1 over n plus 1. And that's your answer. Now keep that in mind, because we just got this out of nowhere, right? This did not exist prior to us mentioning it. With that being said, let's do this all over again. This time with tangent inverse of x. And recall, because I already wrote it for y'all, tangent inverse of x's derivative is just 1 over 1 plus x squared. And again, you can write 1 over 1 minus a negative x squared. And we saw this, I believe that one. Hold on, let me go back because I think I made it to where like we can connect dots. Where are we? Okay. So not for this one, but for this one, I definitely included it right here. So we know this exists as a limit, as this limit specifically. But now we need to figure out for tangent. So let's go ahead and do that. Do the integral of both sides. Let's do left-hand side. Integral from 0 to x of 1 over t squared plus 1. Again, I'm going to go ahead and cheese this since I already did it. It's just going to be tangent inverse of t from x to 0. That means I'm doing tangent inverse of x minus tangent inverse of 0. I forget what tangent inverse of 0 is real quick. Let me just type that into a calculator. Tangent inverse of 0 is 0. Okay. So it's going to come out to 0. So really on the left-hand side, you just have tangent inverse of x. So pretty simple formula on that technicality, but let's go ahead and do the right-hand side to figure out this part. So again, I'm skipping the part where we move the integration around. I'm just going to move it into where it can be from 0 to x of t to n. Okay, dt. This one's a little weird, but not that weird. You can just write it as let's see, you have this bracket of you adding 1 to it, divided by 2n plus 1, and then from x to 0. Similar idea, the convenience of having it x be 0 makes the whole thing 0, so you can just simplify this to be -1 n, and then x to the power of 2n plus 1 over 2n plus 1. And thus, oh, I forgot to box this. And thus you have the summation value for tangent inverse of x of -1 to the power of n, x to the power of 2n plus 1 over 2n plus 1. And that's your answer. Last page. I've held you all hostage. I apologize. Now, we have some algebraic formulas for natural logs and for the arctangent. These formulas, however, are only valid when x is an interval of convergence for the power series. So recall, the idea of power series and its convergence. For this, I did these for you, but if you want to figure out when these converge, you can using the ratio test idea from the unit 1. But right now, I'm not going to worry about that. I kind of want to focus on the technicalities. So, it says, use the power series formula for tangent inverse of x at x is equal to 1, which we are allowed to do, to construct an algebraic formula for pi. Okay, so this one's a bit weird, but it says because we can't really just find when this is equal to pi. Um, I don't even, oh, you plug them in. So no, yeah, you plug in pi to tangent. You don't plug in this, but it says use it as x is equal to 1. I don't know why I had that brain fart. So let's go ahead and do that. Tangent inverse of 1, which we are legally allowed to say equals this when x is 1, is simply just the summation from n going from 0 to infinity of, and I'm going to skip this part because I can, because it's 1, negative 1 to the power of n over 2n plus 1. And we can say that that's just going to be, let's see, 1 and then plus 1 over 3, but negative because it'll be 1. And then plus 1 over 5 because I'm doing 2, and then it's going to be squared, minus 1 over 7 plus 1 over 9, etc. Tangent inverse of 1 is pi over 4. So pi over 4 is equal to this summation. 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, dot, dot, dot. And now I'm going to multiply everything by 4. So I'll have pi is equal to 4 minus 1 over 3, or 4 over 3, plus 4 over 5, minus 4 over 7, plus 4 over 9, dot, dot, dot. And you should get, as you keep doing these values, I'm going to do them right now, you should get a value that's closer and closer to pi's value. I'm just doing those. I get closer and closer. I keep, like, every time I subtract, I keep dipping a little too far, but I still get pretty close from here. Okay. Or you could have just kept in the summation notation if you wanted to. It's the same here. For here, like I said, you just multiply by 4. So you can just write 4 times that summation. Okay. Example 6. Determine the value of the alternating harmonic series 1 minus 1/2 plus 1/3 minus 1/4, etc. So now we have the prompt. Now, what does this look like exactly? Well, this. We have x minus x squared over 2 plus x squared or x cubed over 3, etc. So really, the harmonic series is simply, here, let me write it. The harmonic series, negative 1 to the power of, what is that? I mean, it has different notations, but as long as you start with a negative value, I mean, a positive value, excuse me. And then you do times 1 over n. This is really just 1 to the power of n, where 1 is that replacing that value of x. So that means that, oh, and then you can also allow it to be 1 to make that sum. So we can jump to being ln of 1 plus 1, which is just ln of 2. And that's going to be the sum of the alternating harmonic series in this case. Okay. Last one. Use the power series formula for tangent inverse of x to construct a power series formula for tangent inverse of 2x to the power of 3. So this is just a glorified plugin. Because we have tangent of x, we can tentatively get more specific and just replace x with this full expression. So if I do that, tangent inverse of 2x3, I can just pay attention to here and get the sum, and is equal to 0, infinity, -1, n over 2n plus 1, and you plug in 2x to the power of 3 of 2n plus 1. And from here, you can, I mean, that's technically the answer, but you could, if need be, distribute however you like, especially if it doesn't match an answer choice on a homework. So you do -1 n times 2 to the power of 2n plus 1 over 2n plus 1, and then times x to the power of 6n plus 3, because I'm multiplying the whole thing by 3. I'm just double checking my answer, and I have it. Yes. Now, this is all still with the same caveat that within that replacement, you would replace the inequality as well. It's less than or equal to 2x cubed is less than or equal to 1. So you just divide by 2 in this case now, and then you could cube root both sides, yeah. You cube root both sides, you just get something ugly. You would get -1 over the cube root of 2 is less than or equal to x is less than 1 over the cube root of 2. Alright, so that's gonna wrap up this video, guys. Let me know if you have any questions, and I'll see you all. Oh, test is tomorrow. Don't forget, there's a review. Do the review. Yeah, that's gonna wrap it up. So I'll see you all later. Bye bye.